Okay, so a voiceover for question 7, and this is quite an easy problem to do. We are going to pull this sort of like U-bend apart. We're interested in the stress at the A location, so we can first of all do a little imaginary cut in the A, and notice that there's going to be two stress terms. There's going to be a stress term due to direct stress, and then there's going to be this bending stress. Now the way that as we try to pull it apart behaves, what will happen is that we're in effect get a kind of like pivoting around the corners as I try to pull this bar, and that pivoting will cause that there'll be a tension along the top and a compression along the bottom. So when I do my stress terms and write them out, I'll take a note of that and make sure that I'm using plus and minus appropriately. So the first part is simply the axial stress. So what we're saying there is what's the direct stress. So what's the stress caused by us just trying to pull this thing apart, ignoring any bending effects. So all we need there is the force that we're trying to pull it apart divided by the cross-sectional area of the rod. So what is my direct stress going to be? So I know that I'm trying to pull it apart by 400 newtons, and that this is a cylindrical type rod, so I'll take the diameter, the 0.02 meters, square it and divide it by 4. Let's plug that into my calculator. And there I have my direct stress. Press the eng button to find out what it is in megapascals. Now let's look for the bending stress. So we've already got a model for what we expect to be happening at A. We're expecting this to be in a compression. So we'll go to the engineer's bending equation we got there. I've copied out the equations that I want to use from the formula sheet. So I'm going to rearrange that equation and find what the bending stress is. Notice these values at the top, they're, I guess, to fool us. We don't need them. All we're interested in is how this force is going to create some bending at that particular point. Now the bending will act around the neutral axis along that particular section. So let's find out the bending moment that's being created. So we can see that it's going to be 400 newtons away from the neutral axis, and the distance away from the neutral axis is 0.25. Well, we're assuming that the neutral axis is bang down the middle of our rod. So we've worked out what m is. So m is going to be 100 newton meters. Now for I, so we'll use the second formula. So notice that they give us second moment of area term here using radius. So I need to take my diameter term and divide it by 2 before I take it to the power 4. Okay, that's easy enough to do. Let's plug that into our calculator. So we want to do pi divided by 4, and then 0.02 divided by 2 will be 0.01. So let's raise that to the power 4. And okay, so that gives us the I value, and that will be, we are working in meters there, so that will be meters to the power 4. So we've got our m term, we've got our I term. The y term will be the distance away from the neutral axis, which we're taking to be in the middle of the rod, to the furthest extreme point. So that will be half the diameter. So 10 millimeters, which would be 0.01 meters. So now we've got our y term. So we can rearrange the bending stress equation and find out what the bending stress is going to be. So let's call that subscript B for bending stress. We'll make a note that we expect this to be in compression, whereas the previous stress we expect to be in tension. So minus 100 times by 0.01 divided by the 7.854 times 10 to the minus 9, and that gives us a bending stress of what? Alright, let's press the Eng button, find out what that is. Megapascals. Okay, so we've got minus 127.388 megapascals. Let's round that up to 0.39. So now I've got my direct stress and my bending stress. I've been careful with my signs. I've made sure that they are the correct values. So to work out the principal stress, well, I can't actually see any other stresses going on. I'm basically got this bending stress which is trying to squash it. I've got this direct stress which is trying to pull it apart. I'm just going to add those two stresses up, and that will be my first principal stress. There's no twisting going on here, and there's no sort of shearing going on here, so the other stress term will have to be equal to 0. So let's just add them two up to find our total stress, as it were, at A, which will be our stress max, and we get minus 126 megapascals. And the other stress component, as I said, well, that will just be 0. D, right, so now we want to do the shear stress. So what the equation I was going to use there is this term here. Now notice, because we've got no torsion, so we're going to have we've got no shearing, so well, you don't really even need to use this equation. Basically we know that the maximum stress is going to be half of our maximum shearing stress, is going to be half of our maximum direct stress. But you could plug it into the equation, prove it for yourself. So when you plug it into the equation, you'll get, say, minus 126, take away 0, divide by 2, and then square it, plus 0, and then we want to take the square root of that. So that just works out to be, as I said, the 126 divided by 2. Which works out to be 63 megapascals. And we're done. Quite a straightforward question. Managed to get that done in, what, under 10 minutes.